Welcome back. And now we are like talking about asynchronous parallel block coordinate forward backward algorithm. And let's do it.
Okay. Thank you for the invitation. And today I will be presenting an algorithm called asynchronous parallel block coordinate forward backward algorithm. So I did this work with my supervisor Silvia Villa at UNIJ, and Saveros also, who is working at IIT but started at Roma Sapienza. And so this is the outline, and I will start by a background. I don't know if everybody is familiar with what I will be talking about, so I will try to start by background. It will be really basic for somebody, so bear with me. I don't know, but it will be. And then I will present the asynchronous model and present the mathematical study and result. It's mostly an optimization more than machine learning, but the function we optimize can be found in machine learning setting. So let's start. This is basically the title. So the title only describes this algorithm. So I don't know, it can be new for somebody, but I will try to explain every term here. What is forward, backward? What is asynchronous here? But I can, for a spoiler, this will model the asynchronicity, and this is forward, backward. But I will try to explain from the basics. And generally, in continuous optimization, we try to minimize a function, right? And we place ourselves in a Hilbert space. So the function is, I think, at least continuous, and in the best case, differentiable. So when it's differentiable, the easiest way to optimize is certainly know is the gradient descent. And the gradient descent, you can put it like an operator applied to your previous step. Then you move to the next step. But the problem here, the function has to be differentiable to have the gradient, and that can happen not to be the case. And you can go around this problem by using what we call subgradient descent. Okay, I will not go into detail about subgradient descent, but it's a generalization of gradient for some type of function. But the problem you will get is that the subgradient descent you will lose the rate here. You will have 1 over square root of k instead of 1 over k for the gradient descent. And the solution people came up with, I don't know when, but is to use the proximal point. And the prox is defined as this admin of the function, and you want to be close to your previous step. This is this force you to be close to your previous step. And this conversion 1 over k in the setting of gradient descent. So I have to precise the setting of gradient descent with the same step size. You get 1 over k, because it's important, because Guler proved that actually the prox, you can give me the rate you want. I will give you the step size. Whatever rate, I will find a step size that will attain. So you will say, it's fantastic because you can get any kind of rate approximate. The problem is it's not computable for everybody, for every function. So it's not computable for every function. And actually, if you can compute the prox, basically you can minimize the function. I will show later in the slide what that means. And sometimes in, let's say, machine learning signal processing inverse problem, your function you are trying to minimize is in this form, f plus g, and the g is summable. A simple example is the lasso, where the L1 norm is your g. No, the g is separable, not summable, sorry. Separable, we say separable. And the L1 norm, which is separable, and your f is in this function. So you can say, okay, I will apply the proximal point algorithm. When you apply the proximal point, this is exactly this. But Here your F can be, now your G, the prox of your G can be simple to compute, like the L1 norm here, but the sum are not so easy. And though the sums are not so easy, it can be hard to compute the prox of the sum. And the simple idea, if generally F is differentiable, like in this example, so you make the first Taylor approximation of F, you linearize F, and you compute the prox. So when you do that, this is what you linearize F at your current step size plus G, and you compute the prox. So after some algebraic transformation, you will get this formula. So basically, it's like you're doing the gradient step on the smooth function, mean differentiable function, and then you're doing the gradient step, the prox on the non-smooth function. So this is forward backward. So we call the gradient step the forward step, and the prox step the backward step. And that's what I mean by forward backward. And you can even improve that. You can even improve that by doing what we call coordinate descent on the gradients to diminish the efficiency of your to increase the efficiency. You do the coordinate descent. Instead of computing the full gradient, you compute the partial derivative, and that diminishes the complexity of the algorithm. That's what we call block coordinates, because you do it by coordinates. And now, since the forward backward is explained, now we'll go on to explain the asynchronous model, what I mean by asynchronous. Basically, is this: if you parallelize your structure, this is sequential processing. This is parallelized processing. As you can see, you can process. If you have 5 machines, I will usually set workers instead of machine. If you have 5 workers, you can put them together to work at once, and you will process these 5 sub-processes in one step instead of 5 steps. So this is a simpler parallelization. And there are actually 2 ways to parallelize a system. There is what we call synchronous way and asynchronous way. The synchronous way is that at each step, every machine waits for each other. So let's say it's like you are moving with someone and there is one behind, you have to wait it at each step. So your algorithm in the synchronous case will be as slow as the slowest machine actually. So that's the problem with the synchronous way. So the idea is not to remove this latency by saying, okay, there is no waiting for each other. So it's asynchronous. If a machine or worker finish, you give him a new data and it continue without waiting for the other one. So that's the asynchronous step. So that's what I studied. But consider asynchronicity, you have 2 considerations to take into account. There is what we call the delay, and there is what we call the reading phase. There are 2 considerations. The first is the delay. And what is the delay? I will try to explain what happened. Let's say, for the sake of example, you have a data. This is a simple data. And you have 2 machines, right? You give to each machine the coordinate 1 to update. And the machine 1 is quicker, right? And you have whatever algorithm you have here. You have your information. And the machine 1 updates the coordinates. So the counter moves from 0 to 1 here, right? And then after the machine 2 is trying to update, as compute its gradient at 0, at iteration 0, and it's trying to update. Now the counter should go to 2, but it doesn't have 1 here, because it's just k plus k plus 1. You use k to compute k plus 1. You have 2 here, but you only have 0. So his information is delayed. That's what we call the delay. You say it's 1 minus 1. The 1 is the delay. It's delayed by 1 iteration. So that's what you have to consider in the asynchronous case. And the second consideration is in the reading phase, because there are two phases. In the shared data, there are two phases. There is a reading phase and the update phase. So when reading, you can allow, you can say, okay, when you are reading the data, there is no computation going on. So there is no update on the data. So what you read, nobody is allowed to update the data. So that's the consistent read case. But yeah, putting a lock on the data also can add an extra overhead and latency in your algorithm. So we remove this lock and we say, okay, we are in the inconsistent read. So I will try to explain the inconsistent read. I hope it will be clear. So let's say, okay, we have this local memory here for machine 1. And since it's the vector, you will read the atomic operation is by coordinate. So you read the data coordinate by coordinate. So let's say it's starting reading the first coordinate, right? But while reading the first coordinate, we allow the other machine to update the data. Let's say M2 is updating the second, and M3 is updating the third. So when you read the first, you put it locally, and you move on to read the second. M3 is updating this one, and M2 is updating the other one. And so locally you have this, and you read this, there is no updating going on. So locally, what do you get? You get the first coordinate, which at iteration count 0. The second at iteration count 1. And the third at iteration count 4. So as you can see, there is no consistency in the iteration count. That's the name inconsistent read. So, and the data you read here, there is no data in the past that is exactly this vector. It's not consistent with respect to any vector in the past, but it's just locally. So you have to consider also this when you are dealing with the inconsistent. So I think all the thing is set, and I explained asynchronicity, the forward backward. Now we can talk about the mathematical modeling and the study and the result we got. So as I said, the setting is this one. We have a function we call a composite function, the sum of f and g. F is differentiable, and G is not necessarily differentiable, but they are all convex, and G is separable. And we put ourselves in the Hilbert space, in the direct sum of Hilbert space. And now, just a refresher, because it was at the beginning, so I have to refresh very quick, it's important. This is a prox. This is a prox, again. And an example of prox is the prox of the L1 node, which we call sort thresholding. So the prox, it's coordinate-wise. So you will get a vector, which coordinate is this one. And as I was explaining, if you can compute the prox, you can minimize the function. So let's say you make lambda tend to infinity. This will be 0. So you're computing, you're minimizing gy. So if you know the prox, you can compute you can minimize. So if you make lambda tend to infinity, right? All this doesn't exist anymore. This doesn't exist anymore, so you only have 0. So it's a minimum of the absolute value. And that's what I was saying. If you can compute the prox, you can minimize the function. And now this is an example of prox, and now I will put the algorithm I showed at the beginning. And hopefully it will be clear now. As I was saying, this is the forward backward. It's coordinate-wise, not the whole vector. And this is the delay. Basically, the gradient you have here may be a gradient you compute in the past, not the actual gradient here. So this is what we model the asynchronicity with. You have to take it into account. And the selection of the coordinate to update at each step is random. And the probability can be abstract. And the only thing we ask for is that every coordinate has at least a chance to be to be drawn. Not the minimum pi is not 0. So every coordinate at each step you can has at least a chance to be drawn. That's the only. And since it's in mathematics, you have a sequence, you will create a sequence. Now you want to know, is it a convergent sequence or not? So that's what we do. That's what we did to try to analyze the sequence created by this algorithm. Does it converge or not? And we are able to prove that the convergence, the weak convergence actually, because we are in the Hilbert space, it's an infinite dimension. And this is the step size rule. Okay, tau is the maximum delay. We assume that the delay gradient cannot be infinite, because maybe a machine cannot be late infinitely. At some point it has to update. So the delay is bounded, and this is the maximum delay you can have. And let's say, I don't know if those who are familiar with first order method, if you take tau is equal to 0, basically you're asking your step size gamma I to be less than 2 over Li, which is the smoothness. So you get in the when tau is 0, you are not in the asynchronous case, you are in the normal case, so you get the normal step size. And we prove that this sequence of converge weakly to a random variable because the sequence is random because of the random selection of the coordinate. Converge to a random variable that take value in the Rmin of f, so it converges to a minimum basically, that's what it's saying. We also give a rate of convergence, which is 1 over k. 1 over k, what we want in the gradient case, we recover the 1 over k as I said in the beginning. But you have, of course, a constant here that depends on the delay, as the delta also here. They both depend on the delay. But here, the thing that we find is nice in our case that it depends on inversely linearly. It's not quadratic, it's not exponential. Because in previous paper there was exponential dependence on this, which is not good. And even quadratic dependence, this is also not good. So in our case, it's just linear dependence, so that's nice. And you will see that what that brings in the experiment section. But okay, we can still improve this rate, and we assume this error bound condition. The error bound, okay, let's say the error bound condition is something that's between convexity and strong convexity. It's stronger than convexity, but it's not as strong as strong convexity. So it's in between. If you suppose that error bound condition, what you get a linear convergence. So it's a linear, we mean exponential convergence to the minimum, and the convergence of the iterate are not weak anymore. It's strong convergence. We can prove strong convergence, and also linear convergence of the iterates. So that's the result. And we have some experiment that we use to compare to existing work. So we have the first one, which is the Liu and Stephen White paper. It was that in their paper the dependence on tau is in the maximum delay is exponential actually. And in this paper, which is recent by Fakine, the dependence on tau is quadratic. And you will see that plays a role in the convergence rate. And so I hope it's a little, sorry if it's not that clear. So basically the blue is ours, so it's quicker. You see that we converge quicker than the Canellis and Fakine paper, whereas the dependence in tau is quadratic. And the Liu and White one, the dependence in tau is exponential. So it's so small that it's like it's not moving. But it's still moving, but it's so small you don't see it in the graphic. And if you increase the tau, you get tau to 10, we still better, even more better than the Canelli. Right, is still small. And that's just to increase tau and see how it's increased with tau. Now you can see the step size relatively to tau. If we compare to the quadratic dependence, you see our step size, even the maximum delay of 100 is still reasonable. It's not that crazy. And for the quadratic, it's just 10 minus 6. This is too small. It will not move. And the exponential is crazy. You see, it's really small. That's why the algorithm is like it's not moving. And that's now I will conclude by showing feature one. The idea is to extend this to other kind of algorithm, the Douglas-Rashford, accelerated algorithm, and those kind of stuff. And also maybe even if the linear dependence is better than quadratic or exponential, maybe we can get to a point we can remove the dependence on tau. Maybe we don't know, but it will be better. Also, to consider coordinate dependent delay, because in our case the delay doesn't depend on the coordinate. That this can be a generalization of what we did, and that's it. Thank you.
Thank you for the nice presentation. Is there any question from the room? You go first.
Can you go back to the slide that went, please? Yeah, where you show, if I remember correctly, the step size of the.
Yeah.
Okay, yeah. You told it's more a curiosity actually than. You told that okay, this fact is consistent with the fact that if you have no delay, you essentially recover the condition of convergence. Okay, and if there is no delay, if I remember correctly, the fastest step size is 1 over the Lipschitz constant, right?
No, it's 2 over L.
Yeah, 2
It's 2 over Li.
2 is the maximum.
Yeah.
Is the
Yes, the best one is 1 over L.
Exactly. And in this case, which is the best one?
This is a question we are trying to see. Which will be the best one?
Okay.
According to it will depend on tau. For sure. In our case, it will depend. We are trying to find what will be the best tau.
It's not the 1 over that stuff.
No.
Okay.
We are trying to see what will be the best one.
Okay.
But it will for sure depend on tau.
Okay.
What we are doing, we are trying to see first computationally. That's why there is something they call performance estimation. So I'm trying to see if we can find the best. That's what we don't do.
But we don't have right now an analytic or an analytic expression. We are.
Yeah, no, nothing.
Thanks.
I have a question about the gradient stuff that you consider. Have you maybe thought about introducing some inertia as in Vista, or is it too complicated?
No, that's okay. Let's go here. That's a future work. So as I said, we're trying to consider accelerated method, inertial momentum, those kind of stuff, to see if we can extend it to accelerated method and what does it bring. And in any case, that's what we're trying to see. Maybe normally the accelerated method, you should have 1 over k squared. We have 1 over k, not accelerated. But if you accelerate, maybe you can get 1 over k squared. So we are trying to see if we can do that.
Is there any other query for our speaker?
One.
Oh.
So you improve the rate of convergence, but what about the computational cost with respect to the proximal?
Yeah, the computational cost is the same for the prox, because we don't consider the computational cost, but this is a standard stuff. For example, we don't add some extra stuff. For example, for this one, usually when you say prox, in practice it's the lasso in the L1 norm we use a lot. We don't have extra. It's the same. It will be the same cost that exists in the literature. We don't add additional extra cost because it's just.
For an iteration, the cost is the same as the previous
Yeah.
algorithm.
Okay, so it's there is any other question, we can back again the speaker.